Okay, now let's move to matter. Okay, so matter consists of elements and compounds. And what is matter? So matter is anything that occupies space and has mass. It can exist in three physical states. We have the solid, liquid, and the gas. And two chemical forms. We have the elements and compounds. Okay, so we will discuss everything about matter here. Okay, an element such as gold or mercury is a type of matter that has a unique set of properties and that cannot be broken down into simpler units. Okay, these are elements are already as simpler substances or are already in its simpler units. Okay, they cannot anymore be broken down. Okay, so just like the elements that are actually found in the periodic table of elements. Okay, so those elements there are already on its simpler substance. Okay, they can never be broken down into another simpler units. Okay, so chemists refer to each element with a unique one or two letter symbol. Like for example, C for carbon, AU for gold, AG for silver, okay, HG for mercury. Okay, so and we can find this actually in the periodic table of elements. So this is an example of the elements. You have your gold and the mercury here. Okay, so your mercury is a silvery like element. Okay, and this is your gold here. So this is actually the chemical elements that are actually used in this book. So you have arsenic, it's a heavy metal, which is the symbol of As, and bromine, you have Br, calcium Ca, carbon is C, copper is Cu, chlorine is Cl, fluorine is F, gold is Au. You have your lead, lithium, mercury, nitrogen, phosphorus, sodium, sulfur, and uranium. Okay, so these are our primary elements that are actually used in this book. How about compounds? So what are compounds? Compounds are a combination of two or more elements, okay, that are held together in fixed proportion. Okay, example is you have your water. So you notice that your hydrogen is an element and your oxygen is also an element. So what we mean by compounds? It's actually the combination of two or more elements. Okay, when hydrogen is combined with oxygen, a water is formed, a compound is formed. Okay, that are actually in fixed proportion. That means you have your 2 ratio of hydrogen is to 1 ratio of oxygen. Okay, so there are a lot of compounds that we can have. Like for example, your table salt, that is sodium chloride. That is a compound. You have your seasoning, like for example, the vitsin or what we call the monosodium glutamate. That is also a compound. Okay. Your sugar is also a compound. That is actually an organic compound which contains 11 molecules of carbon. No. You have 12 molecules of carbon, 24 molecules of hydrogen, and 12 molecules of oxygen. Or if, no. You have 11 molecules of carbon because water has been eliminated by that. You have 11 molecules of carbon. Am I right? And no, it's actually 12 molecules of carbon. And you have 22 molecules of hydrogen and 11 molecules of oxygen. So that is actually the table sugar or the sucrose. Okay, so these are the examples of the compounds that are actually used in this book. You have your sodium chloride, this is your table salt. Okay, sodium hydroxide is a basic compound. Okay, carbon monoxide is actually this is a very deadly or a poisonous gas, especially if you inhale this. It will stick to your hemoglobin, thereby competing to the attraction of the oxygen in the hemoglobin. Okay, so if there is a presence of carbon monoxide, it will be replaced by it will replace your oxygen in the hemoglobin. Okay, so therefore this is actually a toxic gas. Okay, then carbon dioxide, we already knew about that. You have nitric oxide, you have nitrogen dioxide, and you have methane, glucose. Okay, this is the primary carbohydrates that are actually produced by the plants. You have your water, hydrogen sulfide that actually present in the geothermal, or what do you call that? Geothermal areas, okay, or geothermal environments. Okay, hydrogen sulfides are there. Okay, that we have also sulfur dioxide and sulfuric acid, ammonia, and calcium carbonate are actually present in limes or in minerals, okay? Like in caves or the formation of the stalagmites and the stalactites. So actually, they are calcium carbonates, okay? And cements are actually made of calcium carbonates. Yeah, building blocks of matter. Matter are actually made up of atoms, molecules, and ions. So what are atoms? So atom is the smallest unit of matter into which an element can be divided and still have its distinctive chemical properties. So all elements are made up of atoms, and it's called the atomic theory. And it is widely accepted scientific theory in the chemistry. Okay, so the elements in the periodic table are actually, they are atoms. Okay, atoms of sodium, atoms of chlorine, atoms of hydrogen, atoms of gold. Okay, so atoms are incredibly small. For example, more than 3 million hydrogen atoms can sit side by side on the period at the end of this sentence. Okay, since they are very small. Okay, then if you could view atoms with a super microscope, you would find that each different type of atom contains a certain number of 3 types of what we call the subatomic particles. So if you are going to cut or to divide the atoms, you can actually divide them and you can see the subatomic particles. Okay, so what are these subatomic particles? You have your neutrons, which has no electrical charge. You have your protons, which is a positively charged, and you have electrons, which is actually a negatively charged, or the electrical charge is negative. Okay, each atom has an extremely small center called the nucleus. Okay, so an atom has a dense center which contains your protons and your neutrons, which is what we call the nucleus. So inside the nucleus, protons and neutrons are actually concentrated there. Okay, and outside of the nucleus are your electrons. Okay, so that is that is uh, the that is the model of the atom. Okay, so each elements are actually unique in atomic number. So what is this atomic number? This is the number of protons in the nucleus of an atom. Okay, like for example, your carbon has a 6 protons because the atomic number of carbon is 6. Your uranium, which has a symbol of U, the number of protons in the uranium is 92. Okay, you have Oganesson, which is my nickname in my YouTube channel. Your Oganesson is element 118 and it contains the protons of 118 protons. Okay, and therefore the atomic number of Oganesson is 118. Okay, then we have also the mass of the atoms. Okay, that is actually concentrated in the nucleus, and that is what we call the mass number or the atomic mass of the atom. Okay, that would be protons plus neutrons. So whatever would be the number of protons plus the number of the neutrons, if you are going to add up that would be the mass or the atomic mass of that element or of that atom. Okay, for example, if you have carbon, your carbon has actually 6 proton and 6 neutron. If you are going to add 6 protons plus 6 neutrons, that would be 12. And therefore, the mass number of carbon is actually 12. Okay. Then, we have also the other elements have the same atomic number but actually different in mass number, and what we call them is actually isotopes. Okay, so other elements, you have the same atomic number, that means the same element, but they only differ on its mass number. Like for example, for carbon, there are actually three isotopes of carbon. You have your carbon-12, carbon-13, and carbon-14. So you notice that in carbon-12, the mass number is 12, okay? For carbon-13, it's 13, and carbon-14 is also 14. And they have actually different uses and also their percent abundances in nature. Okay, your carbon-12 contains 6 protons and 6 neutrons. Okay, your carbon-13 would have 6 protons since they have the same atomic number, so it could have the same number of protons. Okay, so 6 protons, that means 13 minus 6, it has 7 neutrons. Okay, for carbon-14, 6 protons, but how many neutrons? 14 minus 6, that would be 8 neutrons. Okay? So carbon-12 is actually the most abundant isotope in nature. It makes up about 98.9% of all naturally occurring isotopes. Okay? Now let's move to the molecules. So molecules are the second building blocks of matter, and it's a combination of two or more atoms with the same or different elements held together by forces or known as the chemical bonds. Okay, it's just like also your compounds, but your molecules are, these are actually pertaining of molecules if the compounds are actually uh, organic compounds or they have covalently bonded compounds. Okay, the chemical bonds there that exhibited by molecules are more likely to be covalent. Okay, but I will not go deeper about covalency of chemical bonds. Okay, we are just be limited on this definition only. Okay, so example of the molecules is you have your water. Water is actually a molecule. You have methane is also a molecule. Okay, another building blocks of matter is what we call an ion. So an ion is an atom or group of atoms with one or more net positive or negative electrical charges as a result of losing or gaining one or more electrons. Okay? So if this atom or group atoms gain electrons, then it becomes negative. If that atom loses an electron, then that atom or group of atoms becomes positive. Okay? So you have your negative ions or positive ions. And in chemistry, we call the positive ions to be cations, while the negative ions are anions. Okay. Examples of the chemical ions that are used in this book, you have your hydrogen ion, which is actually the primary ions that we measure when we are pertaining to acidity or pH of solution. You have your sodium ion, calcium ion, aluminum, ammonium ion. You have your negative ion, you have your chloride, you have hydroxide, which is actually the basicity of the solution, nitrate ions, carbonate, sulfate, and phosphate ions. These are actually main components or the nutrients, major nutrients if there is an algal bloom. Okay, so but before those topics, okay, so we will just discuss first the ions. Okay, so nitrate ions are actually very important. So you notice that nitrates is also a negative electrical charge ions. Okay, an important example of ion is a nitrate ion. It's very essential for plant growth. Okay, so if you are going to disturb the, like for example, the watershed. Okay, so you notice that the nitrate ions in the watershed, if it is undisturbed, is the loss of nitrate is very small. Okay, but if you're going to disturb it, you deforested the area. Okay, it's been disturbed, then the loss of nitrate increases also. And because of this, okay, because this is an important factor of essential for plant growth, because nitrogen is very essential for as one of the primary nutrients that are needed by plants. Okay, so if 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 there is a loss of nitrate ions from deforested watershed, okay, so some of the plants will not be will not grow, okay, because of the loss of the nitrate ions due to the deforestation, okay, or deforested area. Ions are also important for measuring the substance acidity in water solution, okay, which is based on the amount of H plus and the OH minus. Okay, the H plus here is the hydrogen ions. Your OH is what we call the hydroxide ions. Okay, it contains a particular volume of the solution. And scientist uses the pH, which is actually the negative log of the H plus. So whatever is the amount of your H plus, you negative log it using the calculator and you get the pH value. And this pH value measures the acidity. If the pH is equal to 7, then that would be neutral pH. If the pH is greater than 7, then that is a basic solution. That means that is a basic pH. Like for example, your pure water has a, not tap water, but pure water. Okay, pure water has actually has a pH of 7. Okay, for basic water, like basic solutions, it should be up greater than 7. Okay, a pH of 8 or pH of 9. Okay, but if it is less than 7, then you have an acidic solution. Okay, like for example, those acid rain. Okay, acid rains are acidic rains. Okay, and if more acid rains are actually being poured out, okay, into the streams of rivers and lakes, then your rivers could become acidic also, or even your water or rivers can also become acidic, and it will affect the wildlife there, or even the living organisms there. Okay, then we have organic compounds. Okay, these are actually carbon-containing compounds. Organic compounds are carbon-containing compounds. Okay, and example of the carbon-containing compounds are hydrocarbons. Hydrocarbons are organic compounds that contains hydrogen and carbon only. Okay, example is your methane, which is CH4. Your butane is C4H10. Normally, you use butane to cook your food. Okay, the small, like a small stove. Okay, you use butane in can. Okay, so the chemical formula for the gas there is actually C4H10. That is a butane. Then methane is actually a gas that is actually released when there is a decomposition of the organic matters, or like decomposing uh, a dead body of okay, of animals or even humans. Okay, so other organic compounds are the four types of biomolecules, or the macromolecules that are actually inside the living cells or living organisms, or in our living bodies. You have number one is your carbohydrates. These are actually also organic compounds because they actually contains a carbon on their chemical formula. So from the root word carbo, that is pertaining to carbon, and you have hydrates is pertaining to water. Carbohydrates could be defined as your hydrates of carbon. Okay, your N there signifies how many carbon. Okay, if your carbon has 6, then you multiply 6 to H2O. Then that becomes C6H12O6. Okay, that's why your glucose is C6H12O6. Okay, because it is also an example of a carbohydrates. The example of that is glucose. You notice? So if N is equal to 6, that becomes C6. 2 times 6, that becomes 12. Then you have oxygen is also 6. So that is C6H12O6. Then if there are a large units of carbohydrates, it's not anymore simple sugars, but we will know known as complex sugars, or what we call the polymers. Okay, the polymers are actually mainly organic, or many simple organic compounds that are actually being linked together. Okay, they are larger and more complex organic compounds, but they are actually essential to life. Example of these are your complex carbohydrates. So complex carbohydrates, like for example cellulose and starch, which are actually present in polymers that are actually present in plants and in animals. Okay, so also we have also humans. We have also polymers of carbohydrates, like for example glycogen, which are actually stored in the liver. Okay, glycogen are stored in the liver. Like for example, if our blood glucose level will eventually high after we eat a meal, okay, our blood glucose level becomes high. Your insulin now will be the one to stimulate the formation of the glycogen. So all of the excess glucose that are found in the blood will be converted into glycogen. They will be linked together. Glucose, 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 and other glucose units will be linked together to form a glycogen or a polymer of glucose. Then it will be stored in the liver. Okay. Number two is you have proteins, and proteins play an important or vital roles in the body, and they are actually made up of amino acids. So the building blocks of the building blocks of protein are the amino acids. Okay, but we will talk about that more and more as we go along with this lesson. Okay, so you have your nucleic acids. Example of these are your DNA or the deoxyribonucleic acids, and you have your RNA or ribonucleic acids. So they are formed by the monomers called nucleotides. So when you say monomers, there are actually single uh, organic compounds. Okay, so there are your DNA or RNA are actually formed by monomers of nucleotides. So you have nucleotides, another nucleotides, another nucleotides. Okay, they are actually polynucleotides. Okay, DNA or RNA are polynucleotides. That means they are formed by monomers of nucleotides and are critical for reproduction. Of course, your DNA is the ones that carries our genetic material. Okay, your RNA is the one that will uh, will be the one to synthesize the proteins which are actually needed for reproduction and growth. Okay. Then the last biomolecules is the lipids, which includes the waxes, the oils, and fats, and are very essential for life. Lipids are actually insoluble. And also, the fats that are actually present in the adipose tissue, okay, that we call it as our bilbil, okay, in Bisaya, that is bilbil, okay, that is actually made up of lipids, okay. These are actually triacylglycerols that are actually fats, okay, present in the adipose tissue or the bilbil of our body or in our stomach. Okay, so matter comes to life because of cells, genes, and chromosomes. Okay, so what are cells? Cells are actually the basic units of life. It's the fundamental, structural, and functional unit of life. And the idea that all living organisms are composed of cells is what we call the scientific cell theory, okay, which are actually widely accepted scientific theory in biology. And within some DNA molecules, there are actually certain sequences of nucleotides which are called the genes. Okay? And each of these distinct pieces of DNA contains instructions or codes called the genetic information, okay, which are actually used for making specific proteins. And each of these coded units of genetic information leads to a specific trait or characteristics which is passed on from parents to offspring during reproduction in an animal or plant. In turn, thousands of genes made up a single chromosomes. Okay? Or it's a double helix DNA molecule wrapped around one or more proteins. Okay? So your genetic information coded in your chromosomal DNA is what makes you different from an oak leaf, an alligator, or a mosquito, and from your parents. Okay? So that is what makes you different from other because of your chromosomes or because of your DNA, chromosomal DNA. Okay, that is what makes us different from other people. Okay, or even from animals or even from other living organisms. So this is how our genetic material actually relationship of genetic material to cells. Okay, so human body contains trillion of cells, and that cell is actually contains a nucleus, and inside the nucleus we have pairs of chromosomes, and our pairs of chromosomes are actually we get it from our parents' chromosomes. Okay, and each of chromosomes contains a DNA molecule which actually form in coiled double helix, and in that DNA molecules, these are actually genes that are segments on a DNA chromosomes that contains instructions to make proteins which are the building blocks of life. Now let's move to the changes in matter. Okay, so we have the matter undergoes physical, chemical, or nuclear changes. So these are the three changes in matter: your physical, chemical, and nuclear change. Okay, so for physical change, it's actually changes in the physical form of the substance, but not its composition. Okay, like for example, if you are melting of ice, okay, so you have solid ice melts. The form is just, the physical form changes, but it's not composition. It's still water. You have the solid water, that is ice. If it is liquid water, then that becomes, the ice now melts and turns into liquid water. It's still water. Okay, it's still H2O. The chemical composition stays the same, but only its physical form. Like for example, paper. You cut the paper into pieces. It's still paper. From a whole paper, from a pieces of paper, it's still paper, but you just change its physical form. Okay. Another change in matter is what we call the chemical change, and it is different from physical change because it is also called the chemical reaction. It's a change in the composition of the substances involved. Okay, there's already the change in composition. Like for example, if you are burning your coal, okay, your coal is actually made up of carbon. And if you are going to burn it, you can see smoke, okay, that is actually carbon dioxide. And it releases a lot of heat in the environment. And there is what we call a chemical reaction. And we can depict a chemical reaction by a chemical equation, which shows how chemicals are arranged in a chemical reaction. Okay, so chemical equation can be used to show how substances are rearranged in a chemical reaction. This is an example of the chemical reaction. Like for example, your coal that is made up of carbon plus oxygen from the atmosphere, and you're going to ignite that, then it will be used, or it will be burned and then converted into carbon dioxide. So your carbon now becomes CO2 or carbon dioxide, and it releases an amount of heat. Okay, from black solid, which is a coal, okay, and a colorless gas from the atmosphere, which is oxygen, then you can form another colorless gas, which is also carbon dioxide. So you can say that this is a chemical change because from carbon, it becomes CO2, okay? So now the composition changes. From carbon, it becomes carbon dioxide, okay? Now let's move to the nuclear change, okay? So there are actually three types of nuclear change. When we say nuclear change, this is the change in the nuclei of its atoms. Okay, so there are three types of nuclear change. You have the radioactive decay, which occurs when the nuclei of unstable isotopes spontaneously emit fast-moving chunks of matter. These chunks of matter are alpha, beta, or gamma. Okay, for alpha and beta particles, or even high-energy radiation, like for example, gamma rays, or it could be both at a fixed rate. Okay, so that is radioactive decay. You have your unstable isotopes. Mostly these isotopes are heavy isotopes, like for example, uranium, plutonium. Okay, so those isotopes that are heavy, they have the tendency to be decayed at a certain time. Okay, when they are decaying, they are actually emitting a kind of, or a chunks of energy or a matter, which can be an alpha or a beta or a gamma. Like for example, on this figure here, uranium-238 can be decay, or can undergo radioactive decay, and it will be converted into thorium and releases an alpha particle, which is a helium-42. Or your iodine-131 can undergo beta decay. Okay, it could be converted into xenon and releases a beta particle. Okay, and so on and so forth. So this is an example of a radioactive decay. Okay, your nuclei has been changed now. It's a nuclear change. Your uranium, the nuclei of uranium is actually different from thorium. Okay, the nuclei now changes. Okay. Another one is what we call the nuclear fission. So nuclear fission occurs when the nuclei of certain isotopes with large mass numbers, like for example uranium-235, are split into lighter nuclei, okay, and release energy when struck by a neutron. Okay, so you imagine that there is a heavy isotope, okay, that if you are going to strike it with a neutron, and that heavy isotope will be split into two lighter nuclei. And by this, it also releases a tremendous amount of energy. And that is what we call the nuclear fission. Like for example, your uranium-235, you strike it with a neutron, then your unstable isotope of uranium-235 will be split into two uraniums, or no, when we split into two nuclei, so it could be a lighter nuclei, which could be a krypton or a barium. And because of the splitting of these two, it also releases a neutrons and also a large amount of energy. And this nuclear fission could be a spontaneous reaction, because if you are going to, because you are actually releasing also neutrons. And if these neutrons will also strike another heavy nuclei, okay, then this nuclei would also be split into another, and thereby releasing a large amount of energy. And also your barium could also be split into two, and that formed nuclei will also be strike with another neutrons and will also be split into another nuclei, and so on and so forth, until a large amount of energy has been released. That's why your atomic bomb has a very tremendous effect, okay, when it will be exploded. And also some of the nuclear power plants that had been built, like for example, the Chernobyl, okay, that when Chernobyl has been exploded, okay, it actually releases an amount of energy and also amount of radioactive substances that are very harmful to human health. Okay, so because energy has been released for a spontaneous reaction of the splitting of two of the nuclides. Okay, so the last one would be nuclear fusion. Okay, so nuclear fusion is different because it occurs when two nuclei of lighter atoms, such as hydrogen, are forced together at extremely high temperatures until they fuse to form a heavier nucleus and release a tremendous amount of energy. Okay, so both nuclear fusion and fission releases a tremendous amount of energy. What is different is that for fission, you start with a heavy nuclei. Okay, then for fission, you start with a heavy nuclei, you strike it with a neutron to form a lighter nuclei. Okay, for fusion, you start with two nuclei, which are lighter atoms, okay, two lighter nuclei, and then you fuse them together by extremely high temperatures, and they will form a heavier nucleus and also releases an amount of energy. Like for example, is that what is actually happening in sun, okay? There are actually hydrogen atoms in sun. It could be deuterium or tritium or other isotopes or radioisotopes of hydrogen. Your tritium, deuterium, or deuterium and tritium. Okay? So, if that case, if these isotopes of hydrogen will undergo nuclear fusion, they will fuse together, they will actually form a heavier nucleus, which could be a helium, which is a noble gas. Okay? Like for example, you have deuterium, which is an isotope of hydrogen, and you have tritium, which is also an isotope of hydrogen. If it undergoes nuclear fusion, then it will form a heavier nucleus, which is actually helium, and energy is also released, and also neutron. Okay? Then the last one is that we have the law of conservation of matter. The law of conservation of matter states that whenever matter undergoes physical or chemical change, no atoms are actually created or destroyed. That's why these are actually, if we are going to, that's why chemists are actually using a balancing of equation to account that all atoms involved in many reactions are actually conserved. Okay? There are actually no loss of atoms or destroyed during a physical or chemical change. But remember, in nuclear change, there is a destruction of atoms, okay? So nuclear change is different. You neglect that, okay? Because you're actually destroying the atoms. You're actually changing the nucleus of the atoms, okay? In nuclear change. But for physical and chemical change, no atoms are created or destroyed. And it is actually depicted in an equation that has been balanced, okay? This is what we call balancing equations. If there is a chemical reaction or a physical reaction, we usually balance it. Okay, chemists are actually used to account of whatever atoms or how many atoms are involved in the starting reactants, then what will be the products formed. Okay, we are actually balancing of how many atoms are found in the reactants. It should also be the number of atoms that are found in the products. Okay, so that is how we balance equation during physical or a chemical change.